We have marathons, and a marathon is 26.2188 miles long.
So we picked the topic of marathons because running is something we can all relate to. We've all had to do the dreaded BP run and the bridge run. Everybody knows that speed is involved and you get thirsty during running. So it's kind of a topic that we could apply a lot of math to. And everybody kind of knows that story where my mom's sisters, coworkers, brother-in-laws, cousins, nephew ran a marathon once. So everybody can figure out someone they know that ran a marathon.
Yep. And I have a cousin who's ran a marathon before, and Sam has had her dad ran a marathon, so we can relate to that.
Yep.
So first off, we're going to talk about the history of running. There is a legend a long time ago in ancient Greek times, around the year 1490 BC, there was a very important message that needed to be delivered regarding the Greek victory over the Persian army. And there was a messenger that was going to deliver this message. And this messenger ran nearly 25 miles from the town Marathon to the town of Athens. And this is where the modern marathon came from, although it has changed a lot since when we first heard of it.
Yep. So a few facts about marathons in general. The marathon that we have today is 26.218 miles, and marathons are run all throughout the world. And the average global time for 26.2 miles in 2014 was 4 hours and 21 minutes. So this takes into account male, female, different age categories. It takes into account a lot of different things. And the women's average was 21 minutes slower than the men's average.
Some popular marathons today, what that we know of, is the Grandma's Marathon, and that one starts in Duluth, Minnesota. And another popular one that a lot of people know about is the Boston Marathon. Marathons draw a very large crowd, and because of this, in 2013, the Boston Marathon was targeted by terrorists. And these bombings killed 2 people and injured 264 others. And that's very devastating, but marathons are usually a happy time, and that's another reason why we chose it. Some common injuries when running the marathon include sudden death, hyperthermia, hyponatremia, hypothermia, and glycogen depletion. So first off with sudden death, this one is pretty uncommon, but if you have a heart condition, this could happen to you, or if you're older. And these sudden deaths are mostly related to people who have heart attacks. There are some other freak things that happen to runners where they've had a stroke, something they didn't know about, and it's happened that they died when they were running. So hyperthermia is when your body overheats and you have a dangerously above normal body temperature. This is very similar to a heat stroke, and these are very dangerous because they can cause memory loss. They can permanently damage your brain because your brain is literally frying because your body temperature is too hot. And hyponatremia is when the level of sodium is abnormally low in your body, because when you run, you sweat a lot, and when you sweat, you lose a lot of sodium through that, so it's important to stay hydrated through Gatorade. And I know some people I know that run, they drink pickle juice before they run or after they run, and that has a lot of sodium, and that keeps their sodium level high in their body. Hypothermia is a dangerously low body temperature, and some runners do get that. It's more uncommon. Hyperthermia is more common than hypothermia, but it can happen. And glycogen depletion is another thing that could happen, and this is when the body runs out of energy, which was stored as carbohydrates. So as you see a lot of runners before they run, they eat pasta and a lot of bread, carbs, and this is so their body has enough glycogen to go on their run.
There's a lot of things that you can do to prevent all of these. You can drink a lot of water. There's a lot of different goo packets that a lot of marathon runners eat throughout their run to keep their body, like the nutrients and the electrolytes, all balanced out so that you don't have any of these severe issues. So we looked into many different parts where we could apply math to a marathon, and we found that you can calculate the speed of runners, the instantaneous rate of change, so that would be how much faster they're getting at a certain point, and you can calculate the volume of your water bottle was how we applied it.
So first we calculated the speed of runners, and speed is distance over time. It's a pretty simple math equation. One marathon equals 42.195 kilometers, and this guy, Dennis Comito, he holds the world record for the fastest marathon ever ran at 2 hours, 2 minutes, and 57 seconds, and this time converts to 7,377 seconds. And if you divide this distance over the amount of seconds, you get 0.0057 kilometers per second, and this actually converts to 12.75 miles per hour. And I don't know about you, but I think that's pretty fast to be running for 2 hours straight.
Yep. So then we went into some of the history on the ideas of the math.
So the first guy who actually came up with the idea of instantaneous rate was Sir Isaac Newton. He was easily able to calculate the average slope between 2 points on a curve, but he had trouble finding the slope at one exact point or one instantaneous point. His goal was actually to find the increasing speed on a distance versus time graph. And without getting too complicated, Newton and his contemporary calculated the derivative, f of x, from the function f of x. And there was some debate on what the name should be called, and there's two different names. But f of x gives the slope at any point on the function f of x. The process of calculating the slope or derivative of a function is called differential calculus. And Newton called this instantaneous rate of change at a point on the curve fluxion and the changing x and y values fluence. Newton named this instantaneous rate method of fluxions, but since then we have changed it to just call it instantaneous rate. So first we found the instantaneous rate for Dennis Comito at 15K.
So we we wanted to know how much faster he was getting after 1 hour. So that would be the 60 minutes. So we were solving for f prime at 60. So we looked at this chart and we took his time at the halfway mark, which would be 61.75 minutes. And then you subtract that by the 58.6 minutes, and then you divide it by those two times. So f at 61.75 was when he was at halfway, which is 21.2 kilometers, and f at 58 seconds was when he was at 20 kilometers. So you divide that distance by the change in time, and you get 0.38 kilometers per hour. So that's how fast his rate of time was increasing. His speed was increasing after 1 hour. So that would be about increasing 0.236 miles per hour. So that would basically be the acceleration.
Next, we found the rate of change at 15K for Haley Gerbelassy in 2007, and we used the same chart as we did previously on the previous page. So here's the formula for the instantaneous rate of change.
And then after 1 hour, we wanted to know what her rate of change was. So we used the same ideas with these numbers. And once you plug it all into the formula, you get down to divide the distance by the change in time, and you get 0.36 kilometers per hour squared after 1 hour. So this would mean she is increasing at about 0.22 miles per hour squared. So that's a little bit slower increase than Dennis Comito.
But that's just because Dennis is very, very fast.
So here's some of the history of integration. Archimedes found some of the beginning formulas for volumes of solids such as spheres, cones, and parabolas, and we have to use these volumes equations to integrate to find the volume of different objects.
And his formulas were extremely modern for the times he was living in, and it was quite impressive the stuff he figured out compared to nowadays.
Louisville created the framework for constructive integration with integrals of elementary functions. So he created the initial integration parts and that we still use today. And Hermite discovered an algorithm for integrating rational functions.
So the history of integrating continued. In 1963, Reich made a major breakthrough, and this really influenced a lot of the later mathematicians about the rules of integrating. He published his work on the general theory and practice of integrating elementary functions, which is what we've done in calculus. And like I said earlier, his work has influenced other mathematicians to focus on integration because it's very important. And water intake while running a marathon is necessary. If you do not drink water, you could easily die or your body could overheat. You'll have a lot of bad stuff happening. So here's a chart of how much water you should drink during the marathons for your pace. So obviously, if you look at the bottom, if you run slower, you don't have to drink as much water. But towards the top, if you look, the faster you're running, the more water you need to drink. On average, a person loses 17 ounces of water per hour while running. So you can see that if you're running very fast, you'll be gaining more water than what you're losing, and that's important when running marathons.
So with water comes water bottles, and we wanted to calculate the volume of our Camelback water bottle.
So first off, what we did was we took the water bottle and we graphed it on its side, so we only had half of the water bottle showing, and we made a linear regression line on our calculators mapping in each of the points. And so the volume of the water bottle with integration would be volume equals pi integrating from 0 to 7.5 for the height of the water bottle, and r squared dr. So we found the linear regression line and we put that in for r because that is the radius, the changing x values. And when you multiply that together, you get 38.924 inches cubed. And we used a converter on the internet, and that converts to 654.3 milliliters, and that's roughly pretty close to 750 milliliters, which is how much this water bottle contains.
There's obviously some error because when we drew the graph out, it's hard to account for the thickness of the water bottle and just the overall area of drawing a line around a round water bottle.
So for the second part, we did a different water bottle than the first one, and we tried to pick a water bottle that was more complicated. This way we would need to do integration by parts. So we would have to integrate it in 3 different parts for each of the different lines because the equations were so different from one another. And as you can see at the water bottle on the right, we have part 1 at the top and part 2 That's more of a x squared function, a parabola, and part 3 at the bottom.
So for part 1, this was the top of the water bottle, and the blue line represents the points on the curve that we graphed out. So first we tried a linear regression line on our calculator, which is the red line, and that wasn't super close. So we tried a parabola or an x squared graph, and that was the black line, and that was a lot closer. So that was our regression equation, and we plugged that into our volume to find the volume of the top part of the water bottle. And we got 16.34 inches cubed just for the top section. Then we went down to the middle section, and on the graph, they're a little difficult to see, but the red pluses were the points that we graphed, so that was in a parabola shape, but it had to round off to go back to where the water bottle straightened out. So the x squared graph was the green one, but we ended up using an x to the 4th graph as the yellow line because it was rounded off on the tops. So we plugged that equation into our volume, and we found the area at the middle section of the water bottle, which would be about 9.08 inches cubed. Then we went to part 3, and we put the points in again, and we had our calculator calculate a regression line that was x squared graph. So we plugged this in along the 3.5 to 8.5 because that was the height, and we got about 46.19 inches cubed for that area.
So when you integrate by parts, you have to add up each of the different areas. So we added up the area from 0 to 2, and then from 2 to 3.5, and then 3.5 to 8.5. And we got 71.569 inches cubed. And when we did the conversion for that, that is roughly 39.657 ounces. And this is roughly or approximately 40 ounces for this 40-ounce water bottle. And again, like Samantha said earlier, there is some error with drying it in. We don't know if we had it perfect, or we can't account for the thickness of the water bottle. So that's why it might be off a little bit. It's human error.
So we picked marathons for our topic, and we found a lot of math that can be applied during these 26.2 miles.
And it was good, and it was a good research project, and we really enjoyed it, and we learned a lot about the bad things and the good things that can happen while running a marathon.
And here's our works cited of all the sources we used.